Okay, now I'm actually recording, and I'm going to show some quick comments and make some quick comments about Mars. It's kind of going to be unusual. All right, first, take pictures of Mars at different amounts of power, and an extremely high amount of power in cropping and zooming digitally gave me an image that is kind of like this. Actually, more like this. This is Mars at about 9,000 power. This isn't actually the image I wanted to show you. The best image I've taken so far was something like this. This is Mars at about 9,000 power, around digitally 9,000 power on the screen. So if you could see it with a 9,000 power telescope, it would look something like this. This is, of course, the image printout. This is just by scale. You can calculate the image printout and the power. And if I digitally zoom it further and make more and change the orientation to match the charts, it becomes about this size. So this is Mars at 18,000 power, roughly 18,000 power. A lot of power. And of course I can manipulate the image more and try to get a better image. So that's Mars. Okay, so there's charts that you can run these charting apps that show you different things. They'll show you the orientation. Now I took a picture of Mars. Mars and the Moon were close together last night. I took some different pictures. Even in the morning it was kind of close, but getting further and further away. So I'm going to show some photos of Mars more recently. But I'm going to show you the photo. First I'll show you a close-up photo from a few nights ago, actually then September 1st. And these are photos of Mars. And basically here's one, and this is heavily processed to try to show more atmosphere around the edge. There's a little bit of coloration oddness here. This has been smoothed a bit. I tried to over sharpen everything and find as much details as I could, and you had a lot of digital grit. This is a little bit more true to what an image would be color-wise, and this is more true. Also, could be more true. It can look more like this. Also, this is more true. Maybe with the blue channel put in more than what you would see with the naked eye, because we're enhancing color images. The camera's 70% efficient in color versus a human vision. And this is a little bit more true as what you might see in the eyepiece. So this is Mars at about 9,000 power also. But it gets a lot smaller when you're looking at lower power, and you're just seeing a little bit of shading on it. Now there's these charting programs, and these charting programs, here's the three images together. Kind of oriented the same way so you can see them next to which is your favorite image. So now what I'm going to do is I'm going to go I'll show you a few more photos real quick. This is a binocular telescope. I was trying to take pictures of Mars. Here I'm trying to take a picture of Mars and the Moon. I should say the Moon and Mars together when they were close together. This is the Moon. You can see this is the Moon and Mars below. This is a live shot of me working on capturing frames of it. The orientation is a little bit different than what it was really, because of the way the telescope was set up, the lens was set up, and the way the camera was set up. The orientation isn't quite right. Astronomers aren't always concerned about orientation, but we try to correct the pictures later on so it'll look like a binocular photo, a photo of true north and south in relation to either the planet or the way you're looking at the planet. And north and south changes over time. The planet's true north and south compared to the Earth's north and south, versus our view of the planet, looking at it on a telescope that looks up and down like a binocular. And now, a binocular view, obviously, this is an inverted binocular view, so this will show me the exact orientation of the planet in relation to the Moon. So when I look in, and this doesn't. There's a camera on a camera lens. This is an astronomy camera. And this doesn't show the proper orientation, so I'd have to correct this orientation to match the binocular orientation, which is still not the same orientation necessarily as Mars is in space in north and south in relation to north and south. Because our poles tilt, the planet is moving, and something called field rotation is happening. But don't worry about all these terms, because all these terms are more for astronomy, photography, and astronomers know about this stuff. There's no test. There's no problem to worry about. So here's Mars, a picture of Mars. I try to get a picture of the setup a little bit. iPhone shots. And here's a shot of Mars above the moon, getting further away from the moon in the orientation in the eyepiece. So that's actually the moon in the eyepiece, 32 millimeter Plossl on that telescope, and that is Mars. It's very, very small, 50 times smaller than the moon in size. So you need a lot more power, a lot bigger telescope to see some details, a lot more power. And since I'm trying to show both, if I zoom in a lot, I can't see them both. So I can show you roughly what it looked like in a charting program. We're going to do that. So these are a couple shots I took, and we're going to take another look here at Mars. Later on in the day, the orientation changed and the distance of the planet to the distance of the Martian planet to the moon changed. And this is what they look like in the telescope. This is what they look like, roughly. Depending on your telescopic view, this is what it would look like. This would be Mars. This would be the moon. This is taken at the observatory. And this was Mars all the way in the bottom corner, right down here. And it looked better in the telescope when it was closer, obviously, because I could zoom in a little more. It looked better in the scope. I could see more detail than I can show you in this photo of Mars. The moon, probably more detail also in the telescope, although I didn't look in the telescope, than you'd see in this photo. So this is basically what I looked at this morning. Here's a picture of me looking at Mars. I'll show this shot of me. Here's a shot of me looking at Mars in the daylight. It's getting daylight, but I can still see the moon and Mars. And it's the observatory in the background. And I don't want to get too close to me because I need to shave. And here's a shot I tried to take of Mars and the moon in the same photo. In the eyepiece while I was holding this handheld, holding the iPhone, holding this handheld, holding it up against the truck, trying to get a shot of Mars and the moon at the same time, and then clouds are moving in. So what I'm going to do is I'm going to show you a couple other things about Mars real quick. Charting programs, what we were able to find. And here's like a panoramic shot of the observatory, but it's kind of cut off in the stitching. It's automatically stitched in the iPhone. That's the sunrise over here. And in the clouds, you can see the different clouds, and the clouds were covering the moon and Mars quite a bit. That's the moon. It doesn't look very good in the photo stitch shot of it. The iPhone can't really get you a great shot of it. So what we're going to do is we're going to go to the chart, this chart program. I'm going to show you Sky Safari real quick. And these are, yeah, this is it. This is the program. This is the moon and Mars around the time I took the photo. You can see here's Mars and the moon. I can zoom in, and you can see they're kind of far apart. They were closer together, and when we pull back and zoom out, we can see the relative location. That's what they look like when we're looking at them, but this is if we're looking south. If we're looking directly south, this line here is called the meridian. So I'm going to go back in time and step back in time and show you how the orientation changed. Watch the orientation of Mars, how Mars seems to go on top of the moon. They're actually shifting in their orientation, and Mars is moving in relation to the moon also. The moon and Mars are moving at different speeds. So this is 5 in the morning. They're quite far apart. We're going to back up. We're going to back up by minutes. We're going to go back in time by minutes. 4 o'clock. 3 o'clock. 2 o'clock. 1:30. I'm going to pause it here. So this is closer to the time when I was trying to take photos of it, and I could see it, and I started to take photos around 1:30. I was taking a bunch of photos around from like maybe 1:30, 1 o'clock in the morning. Around 12 o'clock I got a note from a friend who had a photo, a really good camera. I want to do that. I'll look at time. And he showed me a photo of Mars, and it was kind of like this. It was really close, right? And of course, if you zoom in, you can zoom in more with an eyepiece or on the screen and see them both on the screen. You'd see them closer and bigger. And if you look at the orientation the shadow here, we're closer to the eastern horizon, and on the eastern horizon, the orientation of the shadows, because the sun is below the horizon, the orientation is closer to the way the sun would appear. Kind of hard to explain, but Mars is closer to the moon here, but the orientation that I'm seeing in this charting program is showing me in relation to the horizon. There's the eastern horizon in the east. In the northeast it would rise, and the sun is below the horizon. Where is it? It's way down here, right? So it's lighting up these objects. It's not lighting them just in relation to the horizon, but in relation to where they are in relation to the sun in their horizon. So we move in, we see the sun here, but there's also our horizon. So there's three things going on here. It's very complicated. There's something, what's happening is they're taking this arch in the sky, it's called the ecliptic. They're taking this arch in the sky, and see, do we see this here? Well, we don't really show the ecliptic, so you don't really see it. But the arch, you can see, as I back out, if we look in the south, we're going to go forward now. And I'm going to zoom in a little bit. I'm going to put south right below us, right? And then I'm going to play forward. Watch. What you're going to see is you're going to see that if we were looking at the sky, we would see a rotation. If we look at the stars, let's take this box up here for a minute. See this box here? How it's oriented? If I look at over time and I hit play, this box will rotate. Watch. I'm going to go forward. Well, it's kind of hard to explain. It doesn't look like it's rotating because this is a flat orientation, but it really is rotating. Let me hit pause. It's rotating when I look at it directly above the horizon. If I'm looking from the horizon here, see how every time I put the horizon below it, directly below it, this line here below it, it's rotating in a rotational method. So what's happening is, as I'm looking directly over the horizon below it, let me pause here. This is 7:30 in the morning. It'll be pretty bright out, but I'll back up a bit. It's still bright, around 6 o'clock in the morning or whatever. This is the orientation when I look directly over the horizon. This is where it is on the horizon, a little southwest, right? And I zoom in. This is the orientation I would see the planets in. Well, it's shifting, so the orientation is shifting. But the crazy thing about it is they're in the west, but the moon, the sun that is bright lighting them, is in the east. They're not in the east anymore. Check out the shadows. The shadow of Mars, I wanted the shadows to align right and be correctly, and I'm like, well, this photo has got to be wrong. It's got to be inverted or something. The shadow's got to be wrong. I'm thinking of the shadow of Mars being above it, because that's how it was earlier in the day. But it's not. It's below it. How can it be below it? Well, the reason is this shadow is put on the moon in relation to the sun. And the sun is in an orientation that's lighting this part of the moon. So the shadows are true, but unless the moon is close to the sun, you're not going to see the shadows match up in the sky as correctly because of our orientation being different. It's because of a thing called field rotation. It's really weird. So what's happening is the shadows of the moon have been field rotated as the stars field rotate when you're looking at it straight on with a regular binocular, like looking straight up and down, right? And so, if we zoomed in on Mars, we're going to see the same thing. We can actually zoom in and see the chart of Mars from this program, which is very accurate, very cool. So here's the shadowing of Mars. Check it out. You can see details of Mars. They change over time, but here it is. So here's the shadow. Here's the shadowing thing, and I could see faint shadows of it. Like it was like kind of like that, something like that, about like that in the eyepiece, even smaller than that, but with the moon too. And I could see that when they were closer together, I could see that detail. It was interesting to see a little bit of shading detail in the eyepiece and the moon at the same time. Very interesting to see. It doesn't happen very often. It might happen next month. I don't know if it'll be closer next month. It might happen late in the month, but we're near opposition, so right now it happened. The moon goes around and gets close to every planet. Everything on the ecliptic, which is the ecliptic is like an imaginary circle above the equator. But the ecliptic for celestial bodies is not just that. It's the path they take, and they're on the same plane as our equator in the sky. So it's a complicated thing, because you have a globe-like thing that's happening in the sky, but we're seeing these things that are happening. And the funny thing was, I wanted to get this picture of the moon, and I wanted the shading to be right, and I was imagining it was on the east side of the meridian. It was closer to the horizon in the east, so I wanted to flip the picture. So I'm going to show you how that works real quick. So I tried to flip the picture because I wanted to make it true, and I'm thinking that the moon and Mars are on the eastern horizon and the sun's right below it. So when I flipped it from here, I said, well, this can't be right. This can't be the right orientation. The shadow can't be like this. So I flipped it. I flipped the image, and I came up with this. And this is what it would look like earlier in the day if they're at this distance. This is what it would look like, right? Mars would be above, and the shadow would match, the moon rising on the east. But over time, the whole thing rotates in relation to our horizon, because the movement of these things in the sky is based on the Earth's rotation, and we're at an angle. Really hard to explain. It's a three-dimensional concept. I can kind of show you in the charting. It's really hard to explain. You got to see it. When you take long exposure photos, if you take a photo and you take a long exposure photo of an object, as it's moving, something called field rotation will happen unless you have a mount that's aligned with the axis of the Earth. So field rotation will happen, and everything will blur over time. It will all rotate as the frame rotates. The further away you are from the pole, well, actually even at the pole, you'll see field rotation. You'll see field rotation differing depending on how high up and close to the pole you are, or how far away from the pole you are. They even have a thing called a derotator you can put on the telescope. On some advanced telescopes, they have a thing called a field derotator that actually orientates and moves the camera and rotates it as the orientation of the telescope looks at a different part of the sky in relation to looking up and down, like a cannon. It just goes up and down, left and right. A field derotator has to be, that derotates the field, has to hook the camera up and actually move the camera. Professional observatories have it, and amateur telescopes have been able to add that to that, and usually the field rotators that an amateur astronomer has don't work well, and it's a nightmare. So we use a thing called an equatorial mount. But that's another story. I'm just going on and on. We can talk forever as astronomers, and way more detail than you need to hear. So I'm going to stop now the video.